Okay, and onto the activation energy for the following reaction is 432 kilojoules per mole. What is the activation energy for the reverse reaction? So basically, if we draw our chart, our reaction energy diagram, we're going to see that the delta H is negative, which means that the reactants have more energy than the products. So that's kind of what our energy diagram is going to look like. Now, our activation energy, remember, is the difference from where our products start to the transition state. So that's going to be our activation energy. And then our enthalpy is going to be, I'm just going to take the absolute value of the enthalpy, and that's going to be 164. That's going to be our delta H right there. So to find the total energy so we want to find the activation energy for the reverse reaction. So basically, if we go the opposite direction, what we're saying is so it's going to be the same graph, but in this case, we need this entire length. And basically, from this graph, we know that this entire length is going to be our activation energy, 432 kilojoules per mole, plus our 164 kilojoules per mole. And so we are going to add those up, and we will say 432 plus 164 is 596 kilojoules per mole. And yeah, so that's how you do that one. Next one, identify all of the intermediates for the following reaction. So we're given down here, we're given our total reaction. I'm going to change my formula to red now. So NO2 plus CO2 goes to NO plus CO2. So remember, the intermediates aren't going to be reactants, and they're not going to be products. So let's start by taking away everything that's either a reactant or a product. So we can get rid of all of our NO2s. We can get rid of all of our COs. And we can get rid of all of our NOs. And we can get rid of all of our CO2s. So you can see, so we've gotten rid of all the products and all the reactants, and that leaves us with our intermediates. And we only have one intermediate, and that is NO3. Okay, why can a catalyst increase the reaction rate? So A, the catalyst will increase the temperature. B, the catalyst will decrease the temperature. C, the catalyst alters the surface area of reactant molecules. Or D, the reaction alters reaction mechanism and activation energy. So I always kind of like the analogy of using a key on a door as kind of like a catalyst. Like, you could break, if you have a locked door that you're trying to get into, yeah, you can like break down the door, but that's going to take a lot of energy. Or you can use the key in the lock and unlock the door, and that's way easier than breaking down the door, right? So, let's use that analogy, which it isn't a perfect analogy, but I still kind of like it. So if the catalyst will increase the temperature, that would mean that having a key would like set the door on fire. And yeah, it would be easier to break down, but that's not what a key does. Right, a key unlocks the door, so that's not going to work. Again, a catalyst will decrease the temperature. Well, maybe like the door would freeze, which I don't know if you've ever like tried to open your car door in the winter. That's pretty tough. So yeah, it's like if the key made the door freeze, that would be decreasing the rate of reaction, but that's not what a key does. The catalyst alters the surface area of reactant molecules. So I guess that would be like if the key like made the door into kind of like a puzzle sort of. So like yeah, it might be easier to break down the door if like you've taken apart the door and glued it back together, kind of, if it's kind of that, it's a funky door like that, but that's not really going to, that's not what a key does. And the reaction alters the reaction mechanism and the activation energy. So in this case, we're saying like the key is unlocking the door, right? The react mechanism, instead of breaking down the door, we can use the key and unlock the lock. And the activation energy, again, it takes way less energy to put a key in the lock and turn it than it does to break down the door. So that's really what a catalyst is doing. Plot the reaction coordinate diagram for an endothermic reaction with and without catalyst in one diagram. Label each axis, activation energy, reactant, and product for both lines. Okay. So, I'm going to draw one of these in blue and one of these in green. So, an endothermic reaction, that means it's going to be taking in energy, right? So that means our reactants will have less energy than our products. So that's kind of what that's going to look like. And that's without a catalyst. Now, if we had a catalyst, remember a catalyst is going to lower the amount of activation energy needed. So again, they start off at the same point, but they're going to have a lower amount of activation energy. And let's see. So basically this line, this is kind of our initial amount of energy for the reactants, and so the activation energy for the without a catalyst is going to be from the top of that transition state to the initial energy of the reactants. And same for with a catalyst, only it's going to be shorter because that transition state doesn't have as much energy. And then our products, remember, they're going to end up at the exact same place. Here are our products. Our reactants, they start in the exact same place. And let's see, so I've labeled the activation energy, the reactants, the products, and then I just need to label the axes. So remember, the energy is going to be on the y-axis, and the reaction coordinate is going to be on the x-axis. The reaction coordinate is just kind of where in the reaction is, and the energy is the amount of energy that the I guess the molecules in the reaction have at some given point in the reaction. Okay, and that's it for this recitation. Let me know if you have any questions. See you later.